After
Tell me when.
You just decide.
Good evening. I think most of you don't know me. I don't know. But it's a great pleasure to welcome Devika Tharakkal today. She just finished a PhD. She's Dr. Devika Tharakkal. She did a 2-month project with me long back, 2016, I think. And then went to work on a PhD at the University of Newcastle. One of my collaborators is Lord Shukura. She just finished that and is moving on to a postdoc at the University of Helsinki in Finland. She works on galaxies, galactic magnetic fields, interstellar medium. Postdoc is going to be more on radiative transfer in various MSCs. But today she's going to present us with some interesting results on particle instability in galaxies, particularly at steady state. The floor is yours.
Thank you, everyone. Hi, everyone. I'm Devika. Thank you for the introduction. First of all, I want to thank Devika for giving me this opportunity to present my work here today. Today, I'll be talking about statistics of particle stability in galaxies. And as I'm going to say, so that I've been doing about PhD in last couple of years. So I'll start with the motivation. So the main objective of this work was to give a little bit insight into the dynamics of the interstellar medium, which is mainly driven by the three energy components, which is the plasma, the galaxies, and cosmic rays. So the dynamics is basically driven by the pressure forces resulting from these three energy components, all acting in the presence of the galaxy. Here, both magnetic field and cosmic rays, they essentially act as high energy light fields. So they are highly energetic. But in the present, when compared to the dense plasma, these two components can be assumed as lighter fluid. And when a lighter fluid is present in a dense fluid, like if they coexist together, we know that buoyant forces can arise in the system. So this force can result in instability. And this is measured at buoyancy instability, or when you add cosmic rays, it's commonly known as particle instability. And this phenomenon has it plays an important role in today's aspects of physics. So it exists in impact as plasma, and it is of interest in a lot of applications in stars and galaxies. So in the interstellar medium, it can have implications on various physical parameters such as the state height of horizon, star formation rates, and our close speed. So the speaker is known about the effect of this instability on this aspect. So we want to see how the instability develops gradually and see if it can give an insight into understanding these parameters. So I'll give a brief introduction to what magnetic buoyancy is. So already so here I've shown a figure on the right hand side. So it's a magnetized bubble in the plasma. So we have magnetic field inside the bubble, and there's no magnetic field outside. And the whole system is in a pressure balance, it's a equilibrium, and it's an isothermal system. So because of the pressure balance, the pressure inside the bubble is equal to the pressure outside, and this causes a density difference between density difference of plasma inside and outside the bubble. That means inside the bubble, the density will be less compared to that of the band of medium. this results in an upward force. So this is just basically the buoyant force. It's a buoyancy effect. So if the system is vertically stratified, that is, if the density, magnetic field, if they were vertically stratified, they were function of Z. This basically what happens is that the density is supported by a lighter fluid, such as magnetic field of place. And under the right instability criterion, the system which is inherently unstable can give rise to instability. That is the magnetic void instability. And this was first studied in the regime of Eisen by Parker in 1966, including cosmic rays and explained Parker instability. So in Parker's model, he considered isothermal gases as shown in the figure here on the left hand side. So we have a isothermal gases with the magnetic field aligned horizontally in the y direction, parallel to the y direction. And the system has a gravitational force acting towards the middle of the disk, so it is constant gravity, particle system of constant gravity. And the system was in this is a simple model, so this was in an isothermal state, so the temperature is constant for the study. And initially, the system was in a magnetohydrodynamical period, that is all the energy components in thermal gas, cosmic rays, and magnetic pressure, they were all in pressure values for the chosen gravitational profile and density. So, as I said before, the system is inherently unstable, so a slight perturbation can destabilize the system. So, what happens is that as the instability rises, the gas will rise, and this will pull the magnetic fields along with it, as you can see on the right hand side. So, as the magnetic fields are pulled along as the gas rises, these get deformed. So, the initially perfect horizontal field lines will be formed, and they bend and move. And as they move, what happens is that it becomes less efficient to hold up the gas buoyantly, and the gas basically falls down and accumulates near the midplane. So you see localized density maximus near the midplane of the cycles of the gases. So shown in the second figure here, so you can see local maximum of density and the deformed field lines. So since Parker, this instability has been studied in the regime of Eisen by many others. They have looked at the linear dimension of instability with varying parameters. They looked at in the case of various gravitational fields. But we know very little about how the nonlinear state of this instability behaves. So the main objective here was to obtain a nonlinear steady state for this Parker instability and understand how the various components are distributed as the instability saturates. So in order to do that, we use three-dimensional magnetohydrodynamical simulations. So here I've taken a void box, so as shown in the figure. So I take a simulation box in the linear solar visibility region of the Eisen, and the box has a dimension of 4 kiloparsec by 4 kiloparsec in x and y, and they are periodic in x and y too. The box is periodic, has periodic boundary conditions, and the height of this box is 3.5 kiloparsec. That is, from the middle of the box, you have it's the midplane of the Eisen, and you have 1.75 kiloparsec to the top and bottom. And at both the top and bottom boundaries, the boundary conditions is fixed in such a way that it has an open boundary condition. So it allows for the energy components of magnetic fields, density, and all to escape through the boundary. So one of the main effect of this instability saturation is that we expect the magnetic field and cosmic rays to rise up from the box, as I said, and it can escape through the box, through boundaries. So in order to successfully obtain a nonlinear state, we need some sort of source. So to kind of emulate a pseudo source in the system, what we do was we impose the fields, that is density, magnetic fields and cosmic rays, the initial fields are imposed, and we keep them constant throughout the simulation. So they are not allowed to vary in time, and what we actually involve in our simulation is the fluctuations to these background states. So as you can see here, we take magnetic field, which is a sum of imposed magnetic field in the y direction, and fluctuations to this, when I say fluctuations, there's some deviations to these background states. Same for the density, and same for the cosmic energy density, and P is the total pressure, and resulting from its components.
So what do you say solar visibility is like some box?
Yeah, so the gravitational profile that we choose for the simulation of this parameters taken from this Newcastle gravitational profile, which emulates the gravitational constant near the solar receiving model. And some of the other parameters such as rotation rate and all we take in the simulations.
So there is rotation.
Yeah, that's why we need to do it.
And by open, you mean just for the magnetic field, or also the mass loss is allowed?
Yeah, so we allow for the mass deviations to fall down as an exponential with the scale height at the boundary. Yeah.
But from the boundary, the mass can leak out of the box, or?
Yeah, so it is open, so it can vary. So the imposed function will be constant, but the fluctuations can fall off as an exponential in z over h. So the h scale height of that is.
So what he means is there a velocity which is outgoing velocity?
Yeah, we allow for outflow.
Is usage finite at the boundary?
No, we allow for outflow. So we use this we use this EBS boundary condition, which allows for like outflows, but it restricts the inflows.
So one side is not boundary condition. One is not periodic, but other two.
Yeah,
X are periodic.
Yeah, so X and Y is periodic, and Z. So we keep the boundary far enough from the midplane so that we can understand the physics near the midplane well enough without the boundary effects affecting the dynamics. But in the boundary, we want to allow for this losses resulting from the saturation of the instability. So that's why we choose this. So it does allow for outflows and loss.
So these fluctuations, they always much lower level than they.
No. So I think I should have used the word deviations rather than fluctuations. So it's not like small scale.
Yeah, that's what
No, it's more like deviation. So it will be in the nonlinear state as in slides. It can be as strong as the most fields in the nonlinear state. So to talk a little bit more about the numerical setup, the equation. So what we do is, like Parker did, we take the initial state to be in a magnetohydrostatic equilibrium. So we solve this equation here with the gravitational field described by Hood and Moore. Here the parameters A1 and A2 is from their work, which emulates the gravitational field that of the solar system. And in order to initialize the magnetic field and cosmic wave strength in the model, we follow the exact description that Parker used in his work. He introduced two parameters, beta m. In his work, it's alpha and beta. So here we have used beta m and beta cr for the. It is like a parameter which describes the strength of magnetic field pressure and cosmic wave pressure proportional to the thermal pressure, which is sound speed square times the density of the thermal gas. So this is the thermal pressure resulting from the plasma. So we can vary these parameters to change. We can increase beta m or beta cr if you want more magnetic strength or more cosmic wave density. So this is how we use these parameters to solve for the magnetohydrostatic equilibrium, and we solve this equation to get a function instead for all three energy components, and we initialize these fields and keep them constant for all time in the solution. Is that clear?
Initially, everything is magnetohydrostatic.
Yeah. So they
nothing
are
moves, nothing.
Nothing moves.
But there is any perturbation.
So inherently, like if you were to simulate the system like that, the essence of magnetic field makes so if the sum of magnetic field plus cosmic wave is non-zero, the system is inherently unstable. But it might take a long time for its stability to evolve on its own. So what we do is we introduce a Gaussian noise in velocity to kind of kickstart the instability.
Give it a bit of help.
Yeah.
First, you speak some pressure term or because the thickness of the disk is so small, only a particular cosmic wave of particular energy could be actually confined, right? Otherwise, it's like a fast going system.
Yeah. So the initial distribution of the cosmic wave, like we have like a similar distribution to that of the magnetic pressure. So we assume like a fluid model for the cosmic wave, and
you have one equation there.
Yeah. So it's just one equation. The fourth and fifth equation is
energy.
Yeah, it's the energy density for cosmic waves. And I'll get to that equation.
But it's interesting that so this is Come to the first.
Yeah, I think you are allowing fluxes of cosmic
Yes, yes.
scale.
So here, epsilon CR is the cosmic energy density, and CR is the resulting cosmic pressure, and F is the cosmic flux. Yeah, and we have another equation of motion for the cosmic flux. So what we have done here is an isotropic non-frequent diffusion model for cosmic rays, which has this diffusion coefficient tensor by J, which is dependent on the local field direction. So it has a stronger diffusion parallel to the field lines and a comparatively weaker diffusion perpendicular to the field lines. So as I said in the previous slide, these equations that I've shown here is for the fluctuations or the deviations to the induced field. So as you can see, the equation of continuity, we have rho dash, we have the limiting equation, we have the induction equation, we have the cosmic energy density and the flux equation. Here, in the momentum equation and the induction equation, we have this parameter is constant S and omega, which corresponds to the shear rate and the rotation speed of the system. So if you want the system to be a non-rotating system with no shear, we put these two values to be 0. But if you want a uniform rotation of the system, we introduce a non-zero omega. And if you want diffusion rotation, which is implemented as a solution, we put S also non-zero value. That's how we implement the diffusion rotation of the system.
Once you have shear, then put shear periodic boundary conditions.
Sorry?
Once you introduce shear, then you won't have just periodic, but shear periodic.
It's shear periodic. Yeah.
Is it some? That's right. Yeah. Some non-standard. What gauge are you using? There is a meter curl A.
This one.
Yeah.
So this is the diffusivity. We use like a global diffusivity value. Are you talking about the gauge transformation from A to B? Yeah, I can't remember on top of my head what the exact gauge is, but yeah, I can get a bit in the paper. Yeah.
The resistance,
Yeah, it's the standard one that we use for the. So yeah, so for the these equations of motion for the deviations,
where is the initial field that equation?
So yeah, well, I've written down the
capital A is initial.
Yeah, capital A should have
Initial
plus A.
Okay.
So yeah, I written the vector induction equation in terms of vector potential, but when I implement it in the book, it is most field is implemented as the magnetic field rather than the potential. So
that is B plus 1.
Yeah, so it should be what I should do.
Well, B
So the initial most field is in parallel to the y direction, and we have zero values for magnetic field under two directions. So I take this deviation equations and I plug it into pencil tool, which is a 6th order finite difference solver, and I'll move on to results. So first I'll show you a few pictures to give the qualitative or pictorial representation of how this stability would be formed. It's actually. So on the left hand side here, what I've shown is the three-dimensional visualization of the instability development in the case with differential rotation at 3 different snapshots. So at 0.3 gigayear, that is the linear instability, linear state of the instability. That's the growth phase. 0.6 gigayear is when the instability has grown and has slowly starting to transiently move into the nonlinear stage. And 1.6 gigayear is the final nonlinear state. So as you can see, the yellow-green lines are the magnetic lines. So initially they are aligned perfectly parallel to the phi direction, and there are no deformations as you can see. But as we move from the linear to nonlinear phase, that is 0.8 to 0.6 gigayear, you can see that the field lines have started to deform, and then you can see these wave-like structures forming in the field lines. And these wave-like structures start to get stronger and more prominent as we move 0.6 gigayear. And due to the loss of magnetic field, the field strength decreases, as you can see from the color map of the field lines, and the deformations also get bigger as you move further from the growth phase of the instability, or like H non-linear phase of the instability. So as the field lines then deform as expected, the blue, this ice map here, here shows the density distribution in Z, and X is the ZX cross section of the density. So you can see that initially the density has smooth vertically stratified function, but as you move to the transient or nonlinear phase, you can see localized maximum for density. So you can see that the density is accumulating definitely. And you can see this, visually see that there are like pockets of maximum, density maximum. But interestingly, as we move further into the nonlinear state, this well-defined structures vanish, and you can see that the thickness of the disk just like it's more concentrated and it gets narrow. So you can see it's more diffuse here, but it's more well-defined and like it's concentrated near the middle.
This is with rotation, differential. What is it?
So yeah, this three-dimensional visualization is with rotation, but this the nature of the evolution that I've just discussed is consistent in all models. So it evolves similarly in the case of rotation, differential rotation, and
one thing I'm confused by the density concentrations is in X. The way you showed it.
Yeah.
But the Parker thing was concentrations in Y. The picture that you drew.
Yeah, so like in the K numbers will change. So like K, Y also you can see similar structures. So
okay. So there is concentrations in both X and Y.
Yeah. So like on the right hand side, like the two-dimensional curves that I've shown, it's in Z and Y. So you can see.
Right.
So you can see similar density maximas, and like you can see this. So in the first row, I have shown the density for superimposed with the magnetic field lines, and in the top bottom column, I have shown the possible energy density superimposed with the magnetic field lines. So as the instability develops, you can see the field lines deforming, and as you move to nonlinear phase, you can see it's plane-like structures and the local maxima for density. And similarly for the cosmic rays, also like as soon as the magnetic field bends, and you can see this like loop-like structures forming, that means the local VZ is non-zero, which was not the case initially. We had like zero VZ throughout the simulation box. And as soon as the instability saturates, we have a non-zero VZ, which means they have stronger diffusion in the vertical direction. So the cosmic rays will start to spread out in the vertical direction.
But it looks more concentrated. The bottom color thing is
you should also should look at the cosmic energies, the color mapping. So they are like all normalized with respect to the energy density. So if you look at the energy density and physical values, the cosmic energy density is much bigger in the nonlinear state. So like they are spreading out. So I'll show you the vertical profiles in couple slides.
Because they're also leaking from.
Right, but the way it seems more as if concentrated than the actual density.
Both are safe now. Both is your plotting normalized. The denominator is same in the linear and non-linear plots. The color scale is a ratio.
Yes, but here the maxima of these are here.
We can't resolve the number.
Yeah, so this figure is a bit misleading in terms of like the maxima. So this is just to see visually present the rearrangement of this energy. So I'll show the actual evolution physical values of the slides, which will give you the
lines are what? Lines.
Yeah, it is BY takes like super.
And only you have to look at the color to the cosmic ray. Is that what?
Yeah. So the color is cosmic rays and
there you can see it looks like clumping kind of thing.
Yeah, that's what I suppose. That's okay. We'll proceed and come back.
So to understand a bit more about the evolution of this instability, we look at the time series of the two properties. So I've considered 4 cases of simulations here. So the first is the green line. So the green line, which is the case with no rotation, that there's no shear, there's no rotation speed. Then I implement a non-zero rotation in that's omega, which is the case of uniform rotation. And then I implement differential rotation with the non-linear and rotation speed. Then for just to experiment with the different rotation rates. I increased the rotational speed and the shear rate to see how increasing the functional rotation might affect the evolution of the instrument. So here, when you look at the evolution of the RMS values of magnetic and velocity, as I said before, the instability has a linear phase, a transient phase, and minor stable saturated state. So in the linear state, these values are increasing exponentially, and
it's too fast.
Or the scale is too narrow.
Yeah, no, it is like the rate is around 20 to 80%. So it's like the growth rates are comparable to analytical models that are running. So on the x-axis, we have up to 4 gigayears. So the linear phase is very narrow.
Since you ran up to 4 gigayears, you wanted to show the whole thing.
Yes. No, I wanted to show it in 4 gigayears because I wanted to show how the total field saturates, how they vary, like in the photo. Going back to the fluctuation. So what I wanted to say here was that as we include the rotation, no matter whether it's uniform rotation or differential rotation, you can see that the growth rate decreases. So if you compare the slopes of this exponential growth phase, you see that the growth rate has decreased. And this is consistent with the works analytical models before, which suggests that rotation weakens the instability and suppresses the growth rates. It only weakens the instability, it does not suppress it completely. So you can expect the instability to still grow, but on a longer time scale. And as you can see, like in the enhanced differential rotation phase, it takes forever for the instability to grow, and we are still kind of in the growth phase. It hasn't saturated quite yet.
Generally, even in galactic disk, rotation stabilizes the large scale. I guess Parker is enhancing large scale stability.
Yeah. So
maybe that's why the pressure stabilizes small scales, rotation stabilizes large scales. If you go to Pinion Tremaine or whatever, one of the galaxies. But okay, interesting. It actually counteracts the Parker.
Yes. Yeah.
And the last bit, the lowest curve is the one with double the rotation and double the.
This dash.
Yeah.
Yeah, we didn't get any to a point where we can find anything from these ones.
Does it mean that the central regions of the galaxy will have less unstable compared to the outer regions? Or?
I don't think I can say anything from the simulation because the model parameters that I used here, at least the gravitational force that I used here, it's not reflective of the central part of the galaxy. So to draw any conclusions like that would be.
Yeah, I'm a theorist here.
But I think if you have a stronger.
No, it's interesting.
No, because of an exponential case, gravity will slowly change compared to vertical gravity.
Yeah, so I think the parameters.
So you are worried about vertical gravity.
Yeah.
Rotation will come from full. So maybe on this question, you can interpret from here.
Maybe.
No, it will be worth looking at it because, of course, gravity is also stronger. That's why you get a larger rotation in the inner parts with the vertical gravity.
Yes.
But you have kept the gravity the same, but increase the rotation.
Yeah. Vertical gravity at 8 kilometers.
Correct. It's so that it will take a few kilometers. Anyway, we should discuss
change the gravitational field like that. I think the initial states, everything will change, like the initial height, equilibrium condition, like the scale height of the gas, and everything will change. So I don't know how that will manifest itself. Yeah.
I have a nice question. I'm still bothered by this fact that you have a small region. So the cosmic ray, you are not actually resolving cosmic ray in that sense. You are taking them as a fluid with a particular equation.
Yeah. It's not like a big.
Because otherwise, I will expect that one of the biggest evolutions that because you cannot have this high energy, even reasonably high energy at this point. I'm not talking about GEV.
Maybe you have a source in the cosmic.
Otherwise, you should have
So the source that for the cosmic rays we have here is this epsilon CR 0. So yeah, there should be 0. So yeah, it should be epsilon CR and it should be epsilon 0.
So you have a constant source. So theta, you have a source.
Yes. But if you ask me if the source is realistic or like if it has like
if you have something which is forcing, you are constantly injecting some motivation, then I will accept that, because you can say that can be related to supernova and that can be source for cosmic ray also.
Yeah.
Because you say that jetting is related to supernova activity, then you can link them.
Yeah, I think she has a source. So
yeah, so we have this
so then there is no problem.
Yeah. So we have this base like flow function for cosmic rays density and magnetic field, which doesn't go below a certain value. So yeah, as I said, the rotation weakens the instability, and one of the effect of this weakened instability can be seen in the evolution of the total energy components, the magnetic fields and cosmic energy density here. So as the instability weakens, the loss of cosmic rays and magnetic fields from simulation work also is reduced. This is just like it's not surprising. It's just that the weakened instability results in weaker dynamics, which takes less cosmic rays and magnetic fields out of it.
The top and bottom is small BRMS and capital BRMS. Are these different?
Yeah, so the small BRMS is the fluctuation, so like the deviations. So it's actual fluctuation BRMS. The bottom one is the px0 squared plus the px squared plus py squared plus z squared, total field strength. So here in the evolution of the field, magnetic field, this dotted line corresponds to the case with the differential equations in nonlinear. So you can see that it decreases initially to a stronger value, so the loss is enhanced, but after some point it starts to bounce back and we see an increase in energy. And this unique evolution of EMS is actually a result of that we see in our simulation, which actually reverses the magnetic field lines, and it requires a bit more attention. So I'll come back to it in a couple of slides. So keep in mind about this.
Splitting the capital B and small b by horizontal average. How are you writing?
Yeah,
there are three things. One is the B0, original B.
Yeah.
Second is this B field, which is the capital B, I guess.
Yeah.
Which is the XY average field.
Yeah.
And the third is the small b.
Yeah, so the small b here is set equal to 0. So we take this mean field that z equal to 0. So we calculate the mean magnetic field at one plane, and then we calculate the fluctuations from that mean magnetic field at that.
This capital B, I think, is the initial field. That's why it's
Yeah.
Okay, that's why it starts with constant.
Yeah.
Okay.
So here we look at that evolution to see how the instability forms the initial field.
So its decrease doesn't mean energy is decreasing, but some reversals are cancelling it.
Yes, that's what the dotted line is, and this will be more evident in, when I talk about the evolution of P. So before I talk about the nonlinear state, I want to give a brief description about the linear instability that we see in our simulation. So the easiest case to understand and compare, or to do a sanity check of what our model to see what we are actually seeing the linear case is comparable, or like it makes sense with the previous models. We take the non-rotating case of the particle stability, and what I've shown here on the left-hand side of the top panel is the two-dimensional power spectrum of the vertical velocity component for two cases. On the left-hand side is the case with no cosmic rays, and on the right-hand side is the case with magnetic fields and cosmic rays. But in both cases, the total pressure will be constant. So I initialize the strength of both these values, as I said, to beta m and beta cr. So the sum of beta m and beta cr is 1 in both the models, but in one model we have cosmic rays, in the other one we do not have cosmic rays. So when you compare these two models, you can see that the Fourier mode, especially ky, it has changed. It has increased from around 1.6 in the parsec to around 3.2 in the case of cosmic rays. And if you look at the energy in each of these modes, that also has increased. So what it generally tells us is that when you add cosmic rays, it destabilizes the system more. So cosmic rays make the system more unstable. So if you would just have magnetic fields, that's magnetic buoyancy, but if, along with the cosmic rays, the particle stability is more stronger than the case with just magnetic fields. And in both cases, we look at the modes ky and compare it the estimated particle modes from the base analytical model. And our values of 1.6 and 2.2, they are within the upper limit given by Jessup-Jair in 1994 their work. So and I think having added it here, they also do an upper limit for their kx values for estimation models, and the kx values that we obtain from the simulations also agrees with their findings. But so these are the things that we have in agreement with the previous models. But some of the other assumptions that people use to kind of make a linear model of the instability, which we don't see in our simulations, that sometimes people assume that the density times the z square, that rho mu z square is constant throughout the simulation box. This is a assumption that people have when they try to obtain a linear distribution model. We try to visualize this in our simulation model, and we find that this is not the case in our simulation. Another important or interesting thing that we find in our linear mode case was that we took the evolution of mu z in the simulation box at different heights, and we plotted their evolution, and we looked at the growth rates. And we see that the growth rate increases as we move from the midplane of the isometric to the higher altitudes. So this variation in growth rate we attributed to the difference in superposition of different modes at different heights. So if you look at the ky, the time evolution, if you look at the butterfly diagram for the ky, you see that the ky modes also, like the energy in ky modes change, like as we move from one height to another. And so essentially the Fourier spectra has a varying nature as we move from midplane to higher altitude. So the self-dependence of the perturbation is also very not well understood in that.
Even your flows are concentrated towards the top and bottom.
This is something like this self-dependence of the rate. We wanted to look at it a little bit more in detail to see, but we didn't agree on a very robust way to see how we can understand variation well. And we say this is what's happening to the certain place. So that's what I'll say about the linear stage. Now I'll go to the nonlinear stage. So to understand the evolution of instability in the nonlinear phase, I look at the vertical profiles for density, magnetic fields, and cosmic energy density in the three different cases. So from this point onwards, I will talk about the case of flow rotation, uniform rotation, and the differential rotation with the non-uniform rotation rate. I will not talk about the high rotation speed. So first, when you look at the evolution of the vertical profiles in the case of non-rotating system, you can see that the green line here corresponds to the initial state, and the dotted yellow line, which I will see, is the final phase. The dash dotted line, this line here, this line, and the case of density here, which is overlapping with other lines. It's the final stage. So in the case of density, what happens is that, as expected, the vertical profile of the density, it narrows. So the scale height decreases, and the strength of the density near the midplane, the peak of this density increases. So it's like almost starts at 0.6 or something. Increases to more than 0.6 near the midplane. And conversely, when you look at the magnetic field and then cosmic energy density, both these profiles basically flatten out as we move to nonlinear phases. So the scale height increases, And at the end, we basically have like an almost uniform distribution for cosmic rays and electric field, and the strength of these components reduced dramatically. So eventually, at the end of the simulation time for the non-rotating case, what we have was a system which was overwhelmingly dominated by the thermal pressure of the plasma and very little energy input from the magnetic field. So now we move on to the case with uniform rotation. Qualitatively, the evolution is the same, like the vertical profiles is similarly in the case of rotation and uniform rotation. But here, you should look at the time scales. So the uniform rotation case was ran for a longer time. So the loss rates, the time taken for the system to reach its states comparable to the case of the rotation was longer due to the weakened instability. So they took longer time for the system to reach out the gas and magnetic field to get out the gas. And moving on to the differential rotation case, we see that the evolution of density still is quantitatively similar, but it's much less dramatic than in the case with no rotation or uniform rotation. So you see that the narrowing of the density profile is weaker, and it is evolving much slower than in the previous cases as well.
What is the cosmic source of zero? So that those should be whatever you have constant.
Yeah, but it's a question. The answer would be the answer to the question before, because the deviations to the background state is almost as strong as the imposed field. So the imposed fields, while they act as a source, their injection rate or their injection energy is not realistically comparable to the actual injection rate.
He's asking about the cosmic rays.
Yeah, even for the cosmic rays, like the fluctuations is much stronger. Like it's almost comparable to the imposed field that we have. So if you
then your equation is correct. ECR 0 is some value plus constant. Otherwise, its profile should not change, right? Otherwise, you have to grow cosmic rays.
Sorry, I didn't understand.
Also, you are saying that you made some mistake there.
Yeah.
Epsilon CR plus epsilon prime.
Yeah, epsilon CR0 plus epsilon prime.
Yeah, the CR and CR that term you have written down constantly, you are keeping some value, right? So
no, it's the epsilon CR0 is the.
I think it is just initial condition. We have a constant source of cosmic ray.
So the constant source is what I initialize the cosmic ray energy density. They act as this.
You have some constant value, only some fluctuations are there, and you deviate.
Yeah. I don't think
that's what is consistent with the plot.
Yeah.
I don't think it's maintained. CCR0.
ECR0 remains constant throughout the simulation.
Is it the third line? Then of course it's all this constant.
So the third line, density negative cosmic rays, all are maintained all throughout the simulation.
Zero value. Yeah. So what we only move is the fluctuation or deviation.
So whatever density you are showing, that is a total density of the fluctuating deviation.
Rho zero.
The one the figures that you're showing.
So that is the total. So that's
if you are holding like that, then we can't
what are you plotting? That's the
this one. This is the total density normalized to the midplane line. So this is rho zero plus rho prime. This is the total magnetic field strength arising from the imposed field, that is V0 plus fluctuations. So I'm dividing by the value at the midplane.
So I have a question. For some of the thoughts, I see some estimates. So what is the x-axis? I can't picture. It's x-axis. The horizontal axis is x-axis, right?
That's with respect to the height. So this is a horizontally averaged distribution of
but
this.
zero means zero.
Why is it asymmetric for some?
Let us take
For this,
very small.
you mean the asymmetry here?
Yeah.
So in the case,
But what is this case? I can't read. This is a differential rotation.
This is the case with no rotation.
That's happening.
And this is the case with uniform rotation. And this is the case with differential rotation.
Okay. So even in the middle panel, the kilopulse is slightly symmetric. Is it because of the imposed initial perturbations that are
No, I think it's something to do with the homogeneity of the flow. Like at this point, I haven't looked at carefully at the asymmetry. You mean this peak? You mean the peak moving away from setting equal to zero, right? Yeah, we saw this for the different for magnetic fields and velocity as well. So we haven't looked carefully at what causes the asymmetry here. But
it's a random thing because she's not imposing symmetry conditions about the equation.
That's right. But
So it just developed it.
equations are very almost uniformly distributed. That's what I was asking. Is it because of the exposed equation?
The initial perturbations are big, but as you move to the nonlinear phase of the instability, the flows become extremely homogeneous, and like you can expect, like I think it comes from the very homogeneous flows here about the in the nonlinear saturated phase where the flows get much stronger, higher velocity values.
But that means the density is exactly peaking at the center. That's negative to the side. Peak of the negative.
The density is peaking at the center.
Yeah.
Yes. That's what I was sort of focusing on. Density is exactly symmetric and peaking at center. Negative to the slightly shifting. So some of these.
In fact, there are also dips. Right?
Yeah, even the black curve, the nice dip, that's also very symmetric. The lowest panel, middle panel, and the first. Yeah, that's what it is.
This has like
the one below that is a black dotted line.
this one.
Yeah, this one. This is a nice, although very small dip, but a nice symmetric. Other cases have some symmetry.
I'll look into the asymmetry a bit more, but I think it's because of the stronger flows here, like the particular fluctuations of the deviations are stronger in the nonlinear phase. But
if you proceed, then things will become clear.
So yeah, in the case of differential rotation, so as I said, the evolution of the group density is similar, but it is weaker and it's slower. And caustic rays also follow a similar pattern, but the total caustic ray energy density contained in the simulation boxes allow much more compared to the case with no rotation and rotation. But in the case of magnetic field, the evolution of the magnetic field strength has a unique structure. So you can see that as we move from the initial state to the nonlinear phases, you see localized minima forming near the midplane. So if I were to plot more field lines, or sorry, not lines, more profiles for the strength at different times, you will see a systematic generation of the local minima near the midplane, and it will reach to a very low value at around 0.1 or something. I can't remember the exact value. And before it starts to shoot up again. And this again is a result of the reversal of the magnetic field that I was talking about before. But for the case of like at some point in the nonlinear phase, in all three cases, the evolution of magnetic field and cosmic rays follows the general pattern of the instability. That is, that as the instability saturates, the magnetic fields and cosmic rays are pushed out of the box and they leave the box. So to understand a bit more about what causes this, what is the nature of flow in the simulation box as the instability saturates, we look at the vertical force balance and the vertical force in the system. So what I've shown on the right-hand side, the left-hand side here is the force, vertical forces, that is the gravitational force, the thermal pressure force, and the magnetic and cosmic pressure force at 4 different times in the simulation with a differential rotation. So you can see that at the linear stage, the sum of all these pressure force will perfectly balance out the gravitational force. And as we move to nonlinear phases, the thermal pressure force increases and the magnetic and cosmic pressure forces they die down to a near negligible value, which remains negligible for the simulation, the pressure forces. So near the midplane, this means that if there is any flow, this is majorly driven by the thermal pressure near the midplane. And to look at the resulting vertical flows, we look at the horizontally average vertical velocities in the simulation. So here I've taken 2 cases, the case with no rotation and the fixed rotation. In here, we can see that the red color means it is a positive user and the blue color means it's a negative UZ. So if you just look at the top half of this box, in both cases, transiently, the UZ is positive in the simulation. So you have flows going out of the box in the top part of the simulation box in both these models. And to see, so as I said, near the midplane, we have this thermal pressure dominating. So what happens, or what causes this outflows to form the higher orbit, so in the halo. So around this positive flows are formed at heights greater than 0.5 kilopascal. So what is exactly happening there?
So inflows are also allowed. There is negative also at the
It is restricted. So we kind of restrict some of the higher order derivatives of UZ coming into the simulation box. So it's not completely disallowed, but we restrict the inflow. I can show you the reservation. It's not not banned at all. You can still have inflows, but it will not be. It won't be like a numerical artifact. You won't have matter going into the simulation box systematically. To see what happens with the vertical flows, what we look here is the evolution of the pressure forces at different times. So what I've shown here is pressure ratios. That is the cosmic pressure with respect to gas pressure and the magnetic pressure with respect to gas pressure. And we look at the vertical profiles. This is the pressure ratios as a function of sets. So the x-axis is set here, and these are the pressure ratios. And as a result of the instability, you can see that the initial constant values of these pressure ratios, they get redistributed, and both the magnetic field and cosmic field get pushed to the edge of the boxes, and they are stronger near the halo, the higher orbit. And evidently, resulting from this higher concentration of these values in the halo, when we look at the normalized forces at the higher altitudes, we see that this force is more overwhelmed by the non-thermal pressure forces in the halo. So you look at the total force, and if you look at the residual forces at these heights, these forces will be resulting from the cosmic and magnetic pressure forces. And as they die down, the vertical flows also die down eventually.
So it's basically cosmic and magnetic driven outflows.
Yeah. So can be the outflows.
But that must be also because Parker needs all these guys to go out.
Yeah. So even though the UZ is positive here, if you look at the momentum flux, so the total mass output is not that significant. So you have this magnetic field going out, and we have cosmic rays going out, but the total roll times UZ won't be that significant.
So Gaussian is there, so very little density at the top.
The central density goes up. Contrary to outflow, but the density goes up.
So the forces are much more concentrated towards the top and bottom. Where there is no
Only
more
the outer part, that's how this.
Yeah, you remove small amounts of matter outside, but
It's
concentrate
very
inside.
So the flows are more, it has a more inflow nature towards the midplane. So it basically
Ratio, she actually cross the density, we see.
Yeah, it's just Gaussian. It's linear gravity. So it's Gaussian density. There's very little density values near the top.
So now we look at the magnetic field evolution in all these three cases. So we have what I've plotted here is the butterfly diagram for the evolution of Vy and Vx in the three cases. So in the first case of no rotation, we see that the initial Vy, which systematically decreases at all heights, and we see that decaying away to a negligible value at the later times at all heights. And when you look at the evolution of Vx, we don't see any systematic generation of Vx in the non-rotating case. As we move to uniform rotation can cause localized dynamo effects, but see Vx generating in the uniform rotation case. But when you compare the evolution of Vy, they are very much comparable to the case with no rotation. So we have the initial closed field, which decays away, if you look at the total field, it decays away to a maybe to be valid towards the end of the century. But in the case of differential relation, if you look at the butterfly diagram, what happens is that the magnetic field, the B value, basically, it remains constant in the halo for a longer time. So it's sustained for a longer time in the halo, that is at the heights above 0.5 or 0.6 kiloparsec. But the loss of magnetic field near the midplane is enhanced at around 0.6 gigayear. So you can see that the loss of Vy is enhanced. So the buoyant loss of magnetic field is enhanced at starting from 0.6 gigayear. And if you look at the corresponding Vx generation, around the same time where we start seeing an accelerated loss of this Vy, we see a spontaneous generation of Vx, a strong Vx generation here near the midplane, which eventually spreads out to higher altitudes. So we attribute the generation of this Vx to a dynamo shear, and this generated Vx basically through shear feedbacks into the induction equation for Vy and pulls the Vy to an opposite direction, and resulting in a complete reversal of magnetic field from a positive direction to a negative. And it doesn't matter what was the sign of the initial field. So if I started with the negative Vy, it will eventually end up with the positive Vy. So this reversal was universal no matter what the initial sign was. So what you basically see is that we see a oscillation for Vy, and this reversal is also seen in some other runs in our group when we study spark instability with the info samples for dynamo. So it's not just unique to our simulation model. So we are trying to investigate going into this to see if this is a more common effect in similar systems with buoyant forces.
So does this repeat? Have you run it for longer?
So we ran it long enough at long till 4 gigayears. It still is not showing like it's reached the buoyant world that Vy strength is saturating a little bit, but if the saturation is not reached a long enough point to conclusively say that it's not going to per second. But due to time restrictions and we also it was also pulling very localized sharp structures which are smoothly resistant of being really unstable. So we need a higher resolution from the kind of effectively feasibly run it to a stronger time. So, and we had to stop it at some point because we thought 4 gigayears is significant enough, but we don't see any evidence for a subsequent another reversal. We want, from what we see, we want to say that it's going to saturate at this point. And if we were to expect another reversal, we would basically have the instability maybe generate or
So this might help the interpretation in the sense we started from Vy. Yeah. Some Cartesian instability gave you momentarily some sort of Vx there in the midplane.
Yeah. Yeah.
Now shear is acting on Vx to give you further Vy.
Yeah.
Depending on the sign of Vx produced by the instability, will determine the further sign of Vy. It is negative because your shear is negative.
Yeah. So this Vx generation is actually resulting from this unique distribution of Vy. So if you remember the plot here.
So red to blue is not surprising that it is reversal. Suppose out of fluctuation you create some any Vx.
Yes.
Shear will give you in the negative Vy.
So you were more surprised with the spontaneous generation of Vx. So that was basically resulting. So we have in the paper where we discussed this. We have given.
But then it's simply stretching off for all the time, and then if there is an alpha effect and all, then you will come back to the cycle. But if you don't, then it is simply stretching.
But you reverse the initial thing at the same time.
Yes. So if we have a negative, no, but that's just consistent with what Vishal saying. Yes. Okay. But we were more surprised with the spontaneous Vx generation. So it only happens transiently. So if you look at the Vx generation here.
Yeah, it's as surprising as creating a VZ component.
Yes, VZ components generation is not, it's a resulting feature of the pathway. It's just the fields being extended and you can see the localized VZ forming. That is if you take the horizontal average for
so it's not simultaneous. VZ and Vx.
No. So this Vx generation, if you get the butterfly diagram, it gets switched on for a couple of hundred megayears, and then it gets switched off. And then the generated recent Bx basically spreads out. So this positive Bx and the feedback of Bx into the induction equation happens only for a short period of time. And we have actually isolated what causes this Bx generation. It is resulting from a positive correlator in the Bx induction equation, which can be identified from the unique nature of the magnetic field profile. So you have this magnetic field exponential function for this Gaussian function Dy, which has a local maxima in the midplane. But due to this enhanced sustenance of Dy in the halo and the enhanced buoyant losses in the midplane, like you see a lot of loss from the magnetic field in the midplane. For a pi, we see localized minima found in the midplane. So the entire vertical profile of Dy changes in this run. And that results in a positive correlator in the Bx between the vertical velocity and Bx component. That is what causes this spontaneous generation of Bx. And that spontaneous generation is what is feeding back into the Dy through shear. So once we identify that Bx is generating shearing, yeah, that was not difficult to understand. But you were surprised and you were confused as to what was caused to this spontaneous Bx being turned on.
That's like a weak field animal.
Yeah, so we need to, if you look at the coefficients like the size, it is a dynamo, like it's probably some sort of hyperbolic or something, but we don't exactly know how to quantify it.
So spheres you are currently making in the midplane, your flows are concentrated towards the top and bottom.
So you're saying it is feeding back from
So I don't know whether it is directly affected.
We need to talk about it later and later. So basically buoyancy plus dynamo, I just say dynamo, and shear results in a complete reversal of the field here. And because of this, we see that the late nonlinear stages, the direction of the By, if you go from z equal to 0 to the higher altitudes, the direction of By changes sign with height, which is an interesting lesson, and it has possible implication understanding some observations.
So you mean at some fixed time, but let's say 2 gigayears, you can see the blue, but there is some red on top and bottom.
At which model?
Whatever, yeah, the last one. If I take 2 gigayears or something like that,
yeah,
I can see some blue in the center.
Yeah.
But there's also red on the top.
Yeah. So the reverse field is just spreading out like the buoyancy.
So that would have observational implications.
So yeah, there's change in sign, like
change in sign with height.
Yeah.
Because normal stuff would not change in sign.
We expect just one direction, right?
But yeah, very interesting.
So to understand a bit more about the evolution of magnetic field,
I think we should wind up. Yeah, please go ahead. But
we also look at the helicities and alpha diameter coefficients here. So when we calculate the kinetic helicity from the fluctuation distribution here, and we look at the butterfly diagram of this kinetic helicity, we see that it has a complicated structure in Z and time. So it has it varies in time, and it is stronger in the transient stages, that is at around 0.6 gigayear. It is strongest near the halo. And the sign of this kinetic helicity was also interesting because it is positive here, and if you calculate the kinetic alpha coefficient alpha k from this, it will have a negative value, which is not what is expected from other simulation models of this type. So we expect a positive alpha k to generate from simulations of similar type. We also calculate the current helicity from these simulations and the signs of this current helicity, and I'll show in a couple of slides the alpha m calculated from these values. They have opposite signs, which is consistent, but they don't exactly cancel each other out. So we have some sort of positive alpha at certain heights throughout the simulation. And yeah, the signs of both these values change over time as well. Continuous, but yeah, we wanted to see if the values of helicity depends on the strength of the instability. So we changed the initial parameters of magnetic field strength and cosmic strength to see if that result in a stronger or weaker helicity. But what we found is found out that the instability is very weak based on the very weak cosmic magnetic field strength regime. It doesn't generate a flow strong enough to cause helicities, but after a threshold, no matter how much we change, the resulting kinetic helicities doesn't change. So we get a sort of saturated values for the standard SP. But so we don't actually understand how these parameters would affect.
All this is for the one with differential rotation.
Yeah, that's the case with differential rotation. Then we calculate the helicities for this uniform rotation.
Haven't or
We haven't. We just looked at these helicities and dynamo coefficients for the case with differential rotation.
interesting because all you need for helicity is rotation and stratification. That you have to learn the rotative.
So I think I talked most of what I wanted to talk about alpha k and alpha here. So but I wanted to basically see was that alpha k has a unique sign and the top and bottom comes of the box, and it has a complicated structure similar to that of the helicities. And we also calculate the dynamo numbers resulting from this alpha k and alpha m, and to see how the dynamo can be quantified at different heights. So we see that if you look at the midplane, so in the halo we have the high dynamo numbers, which is not we don't understand exactly how that can explain what we see in our simulations. But near the midplane, the dynamo numbers that we obtain is similar, is comparable to what one should expect for a dynamo which generates quadripolar magnetic. So the main conclusions. So as in all three cases, except magnetic fields in the case of differential rotation, the final nonlinear state of our instability was in the near state of hydrostatic with no magnetic field of cosmic phase. So the flow was mainly driven by the thermal pressure, especially in the midplane. We see transient outflows in the system. In the case of differential rotation, we see a complete reversal of the magnetic fields. And this is what I showed in the butterfly diagram. One whole oscillation for the magnetic fields here. For both helicity and okay, we see anomalous sign, which needs to be understood further. And both the field reversal and helicity is not just unique to our model, it has been confirmed with an alternate model that will post that for dynamo, which is work that we doing with another PhD student group. There's currently implementation. So,
More questions. Yeah. Because you just go ahead.
Very interesting. Also, once you go beyond the phase, I guess the question would be how do you justify the assumption in the background balance concept?
Yes, so the total energy, like you're asking if the values that we use or like the time states of injection is.
I can understand why you did. It's easier to maintain this profile, etc.
Yeah.
Otherwise, you really understand part of this class.
Yeah.
But then beyond the nonlinear phase, how do you sort of trust these results?
So
beyond the linear phase, in the nonlinear.
So we did struggle initially to see if it is feasible enough to keep this field components as we use like because it is the energy that we input and the rate of energy injection, it may not be comparable to we don't know what the values actually might be, but yeah, so there might be inconsistencies with
maybe I can understand, maybe there are some external cancers or some
yeah.
But maintaining also the densities and the cost.
So with density, we don't actually see much loss of density from the box. So there isn't that much energy mass input into the simulation. So that doesn't adversely affect our simulations in the nonlinear model. So
it's maintained in the box by gravity, essentially.
Yeah, that's also very
the cosmic rays are decreased.
Yeah. So for the energy input, like for cosmic rays and
Because if you allow the density to also vary, that will also create separate branching, trigger other instabilities. Other interchange modes will also be triggered.
yeah, but I don't think we have like
Yeah, you can't do some bigger scale.
I guess once you trigger everything, I mean, initially you want to trigger something.
Yes.
So you keep things strong enough. But once you trigger something, then you switch off all
So
the sources.
yeah, that's what I have. Suppose you now take the results from the linear phase and start the simulation, but without keeping this constant. All sets of variables.
you need to like
You
switch off the
sort
source.
of churn the system and allow it to grow, and you are going in the exponential curve, and then all variables free.
Yeah, I mean, like we tried with no imposed phase. So we tried with initialized phase and just see how the instability would grow, and it doesn't grow past the transient phase. The simulation would say. So we need some flows for these values.
So the thing is, I think you need to maintain the field
Yes.
for the instability, and you're also doing something to the field because of the instability,
Yes.
because of the reversals. So both things are there. That's why I think the latest stuff, the other guy,
Yeah.
Aziz,
Yeah.
they're maintaining the field with some dynamo coefficient already there.
There is no imposed phase there, so only sources for magnetic phase. So it also doesn't have cosmic phase system. It's a magnetic buoyancy stability. But yeah, there is no it's a more realistic case in some aspects, a less realistic case in some other aspects. So,
True. Because, I mean, ideally what's going to happen, you're going to get some dynamo flow, and then at some stage it's going to become Parker state. After that, it does its own thing, as you said.
but
That could be a more difficult experiment. Sorry, that's it.
yeah, but even with the imposed fields, I think the nonlinear state that we obtain can be trusted because like at least in the early nonlinear stages, like there are some codes which try to do two-dimensional simulation of such instabilities, but like it's not that it hasn't run as long as our simulations have. So they also have some similar aspects of nonlinear states like shocks producing endless degrees of magnetic field. So I think the imposed state doesn't adversely affect our final state, but yeah, the rate of injection and other stuff, it probably can be.
I'm going to take a short question. What do you do for the boundary condition? Densities, I can understand you're on the quarter fixed field, so outflow on the quarter.
So
what about
so the magnetic field, so we allow for the vertical magnetic field, the non-zero vertical magnetic field to cross through the boundary. So it has Ex, By, 0 at x both the boundaries at vertical boundaries, and we allow for non-zero p set.
This small comment, sir. So for the Ex that you saw, that is spontaneously near the midplane, and you determine the alphas that are more concentrated in the low density region, the top and bottom. So I don't think those dynamo coefficients have relevance for this Ex. I think they're too far away.
Yeah, we haven't found any evidence saying that alpha is what.
So it might be completely different reason for the Ex production.
Yeah, so I said alpha to say the sustenance of P5 in the halo, which causes that O-shaped. So we start with the initial Py, which is like this, and we end up with the function for Py, which is something like this during the transient phase, because the fields were more sustained in the higher altitudes, and the buoyant losses of Py near the midplane were stronger. So this basically causes something to we identify this particular structure to cause a positive correlator with the x component of the induction equation.
You have actually calculated that.
Yes.
Right? You have taken the V cross V correlate. Whether it is the cause or the effect is what you are asking. Yes, sir.
Do you have a beta repository for all these codes?
Sorry, can you speak a bit more?
Do you have a beta repository for for all this code and simulations that can be.
So this code is actually available publicly. It's expensive, so you can, it's on GitHub.
Is there also a public archive for like people who wants to go through it?
Yeah, so for the papers, there are 2 papers on, you're talking about the results, right? Yeah, so both the papers are on archive now. I can, if you send me or give me a name, I can send you the.
Okay, last one.
Yeah. So yeah, if you just type in steady states of Parker instability, in galaxies, like I think there should be in on the archive or SIBs.
You can search for a name. Any other questions? Okay, if not, thank you very much.